We can describe a function as either increasing, decreasing, or constant as we move across a graph from left to right. And that's key. We always have to be considering what is happening with the y values, what's happening with the outputs as we move across in a left to right direction. So in the example that we see here, as I move across from left to right, my y values are going down. So that's why we say that that first branch is decreasing. In the middle there, the y values are not changing. They're staying the same. It's staying at 1. So that's why we say it's constant in that middle section. And then once we move to the right-hand side of the graph, we can see our y values are going up as we move across the graph from left to right. So we would say that's an increasing branch. And then even though we have filled in circles at these various locations in the graph, anytime we're describing where a function is either increasing or decreasing, we're always going to use either less than or greater than. The endpoints are never included, because at that location, the graph is neither increasing nor decreasing, nor is it constant for that matter. So we're always going to use inequality symbols if they're necessary without the equal to. So if we look at the first example here, we've got this absolute value function that's been graphed for us, but that's not really important. What's important is we're looking at the increasing, decreasing, and constant locations. Now, I'll jump to the bottom there, since we have no section to this graph that looks like this, where we just have a continuous output value. There is no interval at which our function is constant. Now, as we move across the graph from left to right, on this first part of the graph is where we are decreasing. So this is our decreasing branch. And then again, as we move across the graph from left to right, this is our increasing branch. What's tricky about how we describe where a function is increasing or decreasing is we use the x values to describe where the y values are either going down or going up. So if we start with this increasing side here, for what x values is the graph going up? Well, it starts from x equals 0 right here, and then as long as we keep on moving to the right, this graph continues to go up, meaning its y values keep going up. So we're going to say that the increasing part of this graph is from x is greater than 0. So even though we're looking at the y values to determine whether it's increasing or decreasing, we're going to report our answer based on the x values of where that's happening. And so then as a result, the decreasing part of this graph, the left-hand side, is occurring as long as x is less than 0. Again, take note that I have not put the equal to as part of my inequality symbols as a result of the fact of this change point not being included in either one. The function is neither increasing nor decreasing at that location. In the second example, if we jump here, again, I'm going to use the constant section here just because it jumps out at us as being pretty straightforward there. So if we look at that section, so the graph is staying flat, and so with the boundary points at -2 and at 4, so the same graph that we had looked at earlier, we can say that our graph is constant between x being -2 and 4. So again, even though those circles are filled in, we do not include the boundary points for when a function is increasing, decreasing, or constant. Then this section here is where the function is decreasing. As we move across the graph from left to right, the graph is going down. So again, that dividing point where that happens is at -2. So my decreasing branch is as long as x is less than -2. And then for our increasing branch, well, that's happening over here. So as we move across the graph from left to right, the graph is steadily moving upwards with no indication that that's going to change. So we can say that the increasing branch has an inequality answer of x is greater than +4. So as long as x is bigger than 4, our graph is increasing. So once again, we determine whether it's increasing or decreasing based on what's happening with the y values, but we report our answers based on the x values where those y values are changing. Besides the zeros of a function, the places where the graph crosses through the x-axis, or the locations where a function is either increasing or decreasing or constant, we're also interested in any local minimum or relative minimum and maximum points, or they can also be referred to as critical points. So say we have a function that, as we're going to see in just a second, looks something like this. These two locations here would be examples of critical points, or local minimum, local maximum points. So this one here would be a local or relative maximum, because for its region of the graph it is a high point. And then this one here would be an example of a local or relative minimum, because even though it's not the lowest value of the function for that part of the function, it is a low point. And so in order to find these locations, we've got to graph our function. And we can do that using a graphing calculator. So I encourage you to go ahead and do that. But I'm going to go ahead and sketch out what the result is. Now, because everything is pretty tight to the origin, I'm going to rescale my graph. So I'm going to be counting by 0.5s, or the top. Let's try that again. The top is not going to be 10 on my graph. The top is going to be 5. And then the same thing over here. So I'm counting by 0.5s for each tick mark along my axes instead of by ones. And so if I sketch this carefully and I read it off of my graph, I know that I've got a point here at 1, 0 is my y-intercept, and I could have predicted that by looking at my equation and knowing that when I plug in 0, I get 1 for an output. And then I have a couple other locations here and here, roughly speaking, where the graph comes down, dips down, goes back up, and then again somewhere around here. So we have this as the shape of our graph. So we could find the zeros of this function by using the zero tool on our calculator. We can find the minimum and maximum, the relative minimum and relative maximum points, by using the min or max, minimum or maximum tool on our calculator. And so we've done this in class already, but I'm going to let you do it. I will tell you though that the answer for this relative minimum, it occurs at 1.333, so it's 1 1/3, and the output is, that low point is negative 0.185. And then for this relative maximum right here, we are at the y-intercept, so that happens to be the high point there, so we can say that that's at 0, 1. So again, I encourage you to test out those minimum and maximum tools on your calculator. And of course, if you have any questions with this, we'll go over those in class.